Okay, so this problem we are going to be dealing with salt hydrolysis and the effect of adding salts to water in terms of the acidic or basic properties of them. So in this first problem here we have the salt sodium hypochlorite, NaClO, and we're trying to figure out whether we're going to make the solution acidic, basic, or neutral at the end. In this case we're not going to have to actually calculate it for this problem, we simply need to know qualitatively what it's going to be. So the first thing we're going to do is we're going to take this NaClO and figure out what ions it's going to become. So if we were to add solid sodium hypochlorite to water, it will break into sodium ion and hypochlorite. Okay, since sodium is always soluble, we're going to have a complete breakdown here of this. So now we need to figure out how these two are going to react. So the first one is the sodium ion. If we add a sodium ion to water, the way that it could react by hydrolysis would be to react to form NaOH, and then we would have therefore NH plus left over. This, however, will not happen, and the reason for that is because NaOH is a strong base. If you remember, part of the definition of a strong base is that it is completely dissociates in water. So we won't make aqueous NaOH because the Na plus will not react with the OH minus. It'll stay separate. Therefore, this whole reaction will not occur if you cannot make a strong base or a strong acid by hydrolysis. Therefore, the conjugate, Na plus in this case, of a the salt really of a strong base and strong acid will have no hydrolysis occurring. So nothing will happen here. If we look at the hypochlorite ion and react that with water, we'll notice that it's a base. It's a conjugate base of a weak acid, HClO. And as it does that, it's going to take an H from the water, and that is now going to leave an OH minus. So it's acting as a base, and it's making it basic. This, therefore, will be basic because we have made OH minus. Don't get confused by saying, oh, well, we made an acid. This is the conjugate acid, don't forget. So what matters is that we made OH minus. We've made the solution more basic if we were to calculate the pH. Okay, let's look at the next problem here. In this case, we're dealing with whether adding the salt ammonium chloride makes a solution acidic, basic, or neutral if we add this to water. And the other question too is, what about aluminum nitrate? Let's deal with the first one first. So ammonium chloride will break into NH4 plus, remember it's soluble, because of the ammonium, and Cl minus. Now the Cl minus to react would have to make HCl. Once again, our rules that we cannot make a strong acid or a strong base. HCl is a strong acid, therefore Cl minus will not react to form HCl. The other species we have here is the ammonium ion. Ammonium will react with water. And in this case, ammonium will react with water to form NH3. It will act as an acid and donate a proton to the water and form a hydronium ion, which is our sort of synonym for an H+. So what we really have here is we have the weak base ammonium, or weak acid ammonium, making its conjugate base ammonia and an H+. Since it makes an H3O+, the pH of this, and therefore the solution, will be acidic with a pH of less than 7. Okay. One of the things to keep in mind when you're looking at this is that even though we're making a weak base in ammonia, that does not mean that it is a basic solution. It's the making the H3O+ that matters, right? Every acid-base reaction, we have a conjugate base. In this case, ammonia is our conjugate base. The second problem we have here in front of us is dealing with aluminum nitrate. Okay, that's going to break into Al3+ and nitrate. I could write 3 nitrate, but it doesn't actually matter when we're trying to deal with this qualitatively. So if we look at the nitrate with the water, that is going to try to react reversibly and form HNO3. Well, we pretty quickly realize that this can't be reversible because HNO3 is a strong acid, so this would actually have to go just that way, in which case it isn't going to happen. We don't need to worry about that. The next one, the aluminum 3+ with water, there will be a hydrolysis reaction occurring here. In this case, we're going to have 3 waters reacting to form Al OH, remember hydroxide ions are negative, 3 plus 3H plus. The reason that it does this is that aluminum hydroxide, remember, is not a strong base. The strong bases are any of the alkali metals with OH minus, or calcium, barium, strontium with the OH minus. Given that case, we do not need to worry about the fact that we're making a strong base, and therefore this will happen. It may not happen at a very high level, but it will happen somewhat. And given that it will happen somewhat, we'll make some H+, and therefore the pH of this solution will be below 7, and once again we'll have an acidic solution. The final problem in this set is when we have something, a salt like ammonium cyanide, and we want to know whether that is going to, when added to water, make a solution acidic, basic, or neutral. So we need to look at the reactions again. So this will break up into NH4 plus ammonium and into cyanide, Cn minus. So ammonium, we know from the reaction that we did in the last one, when it reacts with water, is a weak acid, so it will make ammonia, and it will also donate NH plus and make hydronium, therefore that will contribute to it being acidic. Cyanide is a weak base. It will react to make HCN, and therefore an OH minus. A bit of a situation here, because we've said that before we looked, one of them reacted, the other one didn't. In this case, both react. So what we're going to need to do is we're going to need something else to sort of figure out which one is more important. In this case, we want to know, are we making more H3O plus, or are we making more OH minus? The way to do that is to figure out how much each one is going to ionize. And the way you do that is compare the Ks. So the Ka for NH4 plus, and we need to find the Kb of Cn minus, and whichever one of those is larger is going to make more. You'll either make overall net more H plus or more OH minus, since we start with the same amount of NH4 plus and Cn minus as they came together in the salt. So if we look this up, we see that the Ka for the ammonium is equal to 5.6 times 10 to the negative 10th. The Kb for the Cn minus is equal to 2.0 times 10 to the negative third. 10 to the negative third, clearly a lot larger than 10 to the negative 10th. This will react a lot more, and you'll make a lot more OH minus than you will make H plus, and therefore the pH will be greater than 7, and this solution will be basic. Okay, so anytime you have a situation where you have one acid and one base, you need to compare the Ks. One of the special cases to be aware of would be something like NaHCO3. If you have NaHCO3, that will break up in Na+, won't react. Its partner would be NaOH, and we can't make that. But the HCO3 minus is an interesting case because it can react two ways. It can react with water to form H2CO3, and therefore OH minus, and act as a base. The HCO3 minus could also act with water to form H3O plus and carbonate, CO3 minus. In one case it's acting as an acid, in the other case it's acting as a base. We would actually need to look up the Kb of bicarbonate and compare it to the Ka of bicarbonate to find out which one is higher up, and therefore whether it would act as an acid or base. So keep in mind that even if something has only one thing coming out, if it's an amphoteric and it can act as an acid or a base, you're still going to need to compare Kas and Kbs.